Sine and cosine. With the language in place and a video that you can go back and reference, we're now ready to talk about sine and cosine as functions. They're derived from the behavior of the unit circle. So, consider the unit circle drawn below. Note the point P. Let's add a name for the angle in standard position in this figure. So remember, standard position starts at the x-axis and extends in the positive, that is counterclockwise direction. So there's our angle, and we're going to call that angle theta. That is a Greek letter theta. Another angle measure letter you will commonly see is phi, sometimes drawn like that. Okay, so let's take a look at the triangle that's inside the circle here. The vertical side has a length that's equal to the y value of P. Remember, P is a point. P is a point in the x, y plane. So that vertical side has length y. Similarly, the horizontal side there has length x. We don't know what those are. I've clearly implied some values based on this particular angle, but we want to think about this as an arbitrary measure, x and y. The definition of sine of theta is this vertical length. So we say that the sine of theta is equal to y. The definition of the cosine of theta is this horizontal length. It's that distance measure. The cosine of theta is the value of x. With this in mind, how could you rewrite the ordered pair xy corresponding to the point P? Well, if we had xy, and we know that x is cosine theta and y is sine theta, we have an immediate substitution. So the implication is that for any point on the unit circle, its x-coordinate is the cosine of the angle, and the y-coordinate is the sine of the angle. Now, since our point P is stuck on the unit circle, what is the largest and smallest values x and y can ever be? Let's take another look at that image. Think about it for a moment. What is the biggest value that x could be and still remain within the unit circle? What's the biggest value y could ever be? Well, the largest that x could ever be would be 1. It'd be going out to that edge. Similarly, the largest that y could ever be would also be 1. So the sine of theta is very specifically restricted. We could say cosine theta must be less than or equal to 1. Sine theta must be less than or equal to 1. When is sine negative? This is an interesting question. What about cosine? Well, let's go back over to our picture. Rather than thinking about our angle measured to this line, let's add a new one. Let's add a line down here. Maybe we should make it green. This is going to be the terminal side of a new angle, and we're going to call this angle phi. Now, we said that the sine of phi would be is the y value of that point, and the cosine of phi is the x value. So both x and y are negative here. And that has to do with which quadrant we lie in. So because we are in quadrant 3, both x and y are negative. So when is sine negative? Well, it's definitely negative in quadrant 3, but let's go back and look at our figure. If we had an angle, say that our angle phi was shifted over past the y-axis, say we put it all the way over to here, the y value would still be negative. That is to say, the sine would still be negative, and that's in quadrant 4. So sine is negative in quadrant 3 and quadrant 4. The cosine is negative in a different place. Say that this was our angle phi. In this case, we're in quadrant 2. The y value, the sine, is going to be positive. And the x is negative. So the implication there is that for quadrants 2 and also, as we had earlier observed, quadrant 3, the cosine will be negative because that's where those x values are negative. Now let's look at the unit circle again, and I want to label each point of the circle according to your new definitions of sine and cosine. So we had previously gone through and ticked these off saying, oh yeah, we start at 0 degrees, and then we've got 30 degrees, and then we've got 45 degrees, etc. So I'm going to keep doing this. You should do it on your own time and or speed up the video. So for each of these points, it's got a sine and a cosine value. So if we were to zoom in and get a little more granular here. For instance, the coordinates of this point at 30 degrees would be cosine 30 degrees, sine 30 degrees. Similarly, the point here, cosine 45 degrees, sine 45 degrees. Once more, I'm going to continue labeling the entire circle this way. Frozen notability. There we go. Maybe. Okay. Okay. Apologies. Let's keep on going. Okay, and then remember our last angle measure is 360. So of course we have the cosine of 0 degrees and the sine of 0 degrees, as well as the cosine of 360 degrees and the sine. Now, we have symmetries galore in this figure, and it's worth asking ourselves what values of sine and cosine must be equal. Well, to do that, we just have to identify what angles have the same x and y corresponding values. So let's, for example, think about that pair right there. Maybe we can get a little bit better. Definitely we need a thicker line to show this. Okay. Here we go. Okay, so because these two have a common x coordinate, what we can say is that the cosine of 45 degrees must equal the cosine of 315 degrees. And we can identify some other relationships. Now, the sine of 45 degrees does not equal the sine of 315 degrees, but we can say that the sine of 45 degrees equals the sine of 135 degrees because they share a y value. Those 2 points have the same y coordinate. Now, determine the values of the following trigonometric functions. Think triangles, but also think position. We can do some work here that just looks at where things are located. So we were told to find the sine of 90 degrees. So let's scooch up. The sine of 90 degrees, that is the y value, right? Sine of 90 degrees, that's the y value. So just by common sense, we'll do a little bit of erasing. Just by common sense, we know that at 90 degrees, well, we've got the cosine of 90 and the sine of 90 is the ordered pair. The x is 0 right there, and y is 1. So what that means is that the sine of 90, because it's the ordered pair 0, 1, sine of 90 degrees must be equal to 1. Okay. Similarly, we can, again, use our common sense here. The cosine of 225 we were asked to find. So this fine value right here. We're looking for the x coordinate there. So we want that chunk. Now, let's use our geometry. Let's use our triangles. We know that we are dealing with a figure. Let's sketch it for ourselves again over here, okay, where the radius is 1, and we know that this value and this value are equal. So we know then that by the Pythagorean theorem, x squared plus x squared equals 1. So 2x squared equals 1. So then x squared equals 1/2, and x equals plus or minus the square root of 1/2, better known as plus or minus root 2 over 2 if you want to rationalize it. Now, I'm keeping plus minus in here, and yet it's the leg of a triangle. So why does Mr. Vish think we should have a negative? Well, Mr. Vish thinks we should have a negative because the leg of this triangle was actually a distance measured out on the x-axis, and it's on the negative x-axis. So we in fact need to use the negative version here. So our final answer is that x equals negative root 2 over 2. Yeah, which if you think about what we did at the very beginning stuff of 7.1, that corresponds to a 45, 45, 90 triangle. That's what we should hope. So then for sine 60, we should be able to get something out of this that's very pretty and convenient as well. 60 degrees. Showing up there, sine of 60 degrees is the y component. We know that our hypotenuse is 1. Okay. Let's use our properties of a 30, 60, 90 right triangle. We know that if this is side S, then this is 2S, and this is S root 3. Okay, but we also have other things that these are equal to. We know that 2S is equal to 1. We know that S root 3 is equal to y. That's actually the sine value we were looking for. So this might actually be enough for us to work with. We could say that y equals, well, if 2s equals 1, then 1/2 should be s. And that will give us y equals root 3 over 2. So what we can say then is that the sine of 60 degrees is root 3 over 2.